problem 2.6 sort of emphasizes something that's actually very important. I sort of can't stress enough just how important this is, and it's the idea of sort of phase constants in quantum mechanics. Before we actually go into that, let's just do this problem all the way through, and then we can talk about the significance of this afterwards. So 2.6 says that although the overall phase constant, which is our time-dependent stationary state, which is psi of t, which we have sort of ignored this entire time because it sort of takes the magnitude squared of this term sort of just goes to 1. This is the overall phase constant of our wave function, and this has no physical significance because it cancels out whenever we calculate anything, because calculating any sort of measurable quantity obviously requires us to calculate the expectation value in quantum mechanics, which requires taking the magnitude squared of our wave function. So this thing just normally cancels out. However, the relative phase of the coefficients do apparently matter. So apparently, if we have something like this, psi of x comma 0, and we have it being composed of a linear combination of two stationary states, apparently the phase constant, or the phi term for these individual stationary states, apparently does in fact matter. And to show that, we already know that, phi of t takes sort of the form of an exponential to the power of I times some function, let's call it f of t. So what we're going to do is we're going to attach an arbitrary phase, and this is a little bit confusing notation. They're saying, okay, we're going to attach a phase of the form e to the I phi. Phi here is not the sort of the phi that we're describing here. Phi is just an arbitrary function of time, which is what I'm describing as f of t. So what they're doing is that they're basically saying, okay, psi of x comma 0 is in fact equal to a times little psi 1, so the first stationary state in x, plus little psi 2 times little phi 2. So we're attaching sort of the phase constant, or what we've been describing this entire time, the time-dependent stationary state, to psi 2 instead. And we're saying apparently this does actually change things in the bigger scheme of things. So whereas the overall phase of this thing, which would be like if we found the time dependency of psi of x comma t later on won't matter, this apparently does matter. And once again, the implications of this we'll cover once we actually finish the problem, but for now let's just do this and see whether or not this actually gives us different results when we do all the calculations that we did back in 2.5. So let's sort of start right away with normalization. So first off, let's see whether a actually changes or not. So psi of x comma 0 is going to be equal to a times psi 1 plus e to the power of I phi times psi 2. So let's normalize this to start with in order to sort of find a. So a squared, or the magnitude of a squared, I suppose would be more accurate, times the integral from 0 to a, because we're in a square well still, of, let's see, psi 1 star plus e to the negative I phi times psi 2 star multiplied by psi 1 plus e to the positive I phi psi 2. This whole thing, dx, must necessarily equal 1 due to normalization. That is a very horribly written d, I apologize. Let me just rewrite that. Okay, so let's do sort of the distribution that we always do. So this is going to be an integral of from 0 to a of, well, we have magnitude psi 1 squared, because psi 1 star times psi 1, plus, let's see, psi 1 star, okay, so let's do e to the I phi psi 1 star times psi 2 plus e to the negative I phi of psi 2 star times psi 1 that is a very horrible psi1. My apologies again. Psi1 plus, and let's see, e to the negative I phi times e to the positive I phi cancels out to 1, and we have psi2 star times psi2, which is just magnitude psi2 squared. And this whole thing enveloped by the dx. We attach our magnitude a squared at the front, and this is supposed to equal 1. So sort of instantly, hopefully you see, so e to the I phi does not have any x dependence, so we can just sort of move them right out of our integral once we split this into 4 parts. Obviously, in that case, then psi1 star times psi2 is going to integrate to 0 because, you know, because of the fact that they're orthonormal, orthonormality, as we've sort of talked about in 2.5. Same thing here, e to the negative I phi sort of moves out of our integral and doesn't do anything, and then psi2 star times psi1 just cancels out to 0, so we're at the exact same point as we were back in 2.5, and we could just instantly conclude that a must necessarily stay the same, and it equals just 1 over square root of 2. So far, we're not seeing any differences. So far, everything is still the same because our sort of normalization constant, which is the only thing we've calculated so far, is the same as 2.5. Now that we've found our normalization constant A, let's move right along to the next step, which is to find psi of x comma t, the more general wave function. So we already know from before, we can just define psi of x comma t as a linear combination Cn psi, whoops, my handwriting is especially messy today, little psi n times phi n times Cn. And this is another mistake. It's not Cn, it's an index according to n. And from here, we already figured out how to find Cn from earlier. We used Fourier's trick. So Cn is evidently equal to the integral from 0 to a of the associated psi n multiplied by psi of x comma 0. So if we plug this in, this is evidently an integral from 0 to a again of, and apologies, there's supposed to be a complex conjugate here, it's psi n star multiplied by, and then we're going to move our a out as before, and then now we have what, psi1 plus e to the I phi times psi2 dx. Once again, sort of the e to the I phi moves out of the integral because it has no x dependence, and the way we solve this is the exact same as in 2.5. So we're just going to do that. So C1, just from looking at this, is obviously just going to be equal to a, which is 1 over root 2. And then C2, well, we're moving the e to the I phi out of the integral, and then everything sort of cancels out again due to orthonormality. So we have a times e to the I phi, which is equal to 1 over root 2 times e to the I phi. And then all subsequent n's equal just 0 because of orthonormality. So from here, if we write this out fully, psi of x comma t is equal to C1 little psi 1 little phi 1 plus C2 little psi 2 little phi 2. And if we write this out fully, we'll start off by sort of, let's see, so this is going to be 1 over square root of 2 times square root of 2 over a, which is the coefficient in front of the psi 1 terms, times sine of n pi x over a. Since n is 1 here, we just have sine of pi x over a. And then we have our e to the power of, I think this is negative I omega t, which we already found in 2.5. Look back there if you're not sure how I'm getting these values. And we're adding this with 1 over root 2 times square root of 2 over a times, let's see, what is this? Sine of, and here n is 2, so 2 pi x over a and then multiplied by our e to the I phi as before, and also our e to the negative 4I omega t. So we can do a bit of simplification here. First off, the root 2 and the root 2 at the top sort of cancel, and then we can bring out 1 over root a. So this is going to equal 1 over the square root of a multiplied by sine of pi x over a added with sine of 2 pi x over a, and then e to the power of I times, let's see, phi minus 4 omega t. And so evidently this is sort of the first time where we're getting something different. Before, in 2.5, we did not have the e to the I phi, it was just e to the negative 4 omega t. Whoops, I just realized I forgot to include the exponential time-dependent factor here. My apologies, e to the negative I omega t is supposed to go right here. Okay, but yeah, so back to my original point. Evidently, this is the first point here where we're getting some differences. Originally, we did not have this e to the I phi minus 4 omega t. It was just e to the negative 4I omega t. So we have this extra phi term. We don't necessarily know what exactly that actually means, but let's just sort of keep on going with our calculations and continue on. So the next step is then to find the magnitude squared of this expression. So the magnitude of psi of x comma t squared, comma t squared, and this is obviously going to equal, so we have 1 over a, because 1 over square root of a squared is just 1 over a, and then we have our sort of long algebraic expression that we're going to have to write out. So we have, starting off, in fact, it'll be easier if we just sort of copy paste this whole thing. Just write it with this. And remember, we're taking the complex conjugate first, so all these negatives at the front go to positives, and this one becomes a negative, so e to the negative I phi minus 4 omega t. And this is going to get multiplied by the original expression, which is just, whoa, okay. Canvas is getting a little bit small. Let's make it a little bit larger. Make this a little bit neater. So we're multiplying by this. So I'm gonna add this little multiplication dot symbol here. And if we write this out fully, well, okay, so we have 1 over a at the front again. And we have a lot of expressions that we have to write out. So let's start off with 1 and 1 right here. So this is just e to the I omega t and e to the negative I omega t cancel out to 1. So we have sort of sine squared of pi x over a. And then let's do 1 on the top and 2 on the bottom here. This is going to give us sine of pi x over a times sine of 2 pi x over a. And then we have e to the I omega t times e to the I times phi minus 4 omega t. So this is, once we multiply exponentials, the exponents add. So this is going to be e to the I of phi, and then we have minus 4 omega t plus omega t. So this is going to be phi minus 3 omega t. And now let's do term 2 over here times term 1 on the bottom. So that's going to be plus, let's see, sine of pi x over a times sine of 2 pi x over a And then we have e to the negative I times phi minus 4 omega t. So this is going to be e to the power of, and we can just sort of take the negative I and move it out to the front, and the inside is the exact same. It's going to be phi minus 3 omega t. And finally, we're going to add the final term, which is just sort of same as the first term, sine squared times 2 pi x over a. And then the exponential just cancels itself out. And we're going to do the same thing as before, where we're going to sort of get rid of this exponential by using Euler's law to turn this into purely trigonometric function. So we have sort of, this is going to become, let's see, this is going to be 1 over a times, and we have the same thing at the front, sine squared of pi x over a. And we're going to distribute out the sine times pi x over a times sine 2 pi x over a. And then we're going to multiply by, let's see, e to the I times phi minus 3 omega t plus e to the negative I times phi minus 3 omega t. And finally, we're adding, once again, at the end, sine squared of 2 pi x over a. And at this point, we now use Euler's law on this thing and get that e to the ix is equal to cosine of x plus I sine of x. Once we sort of do that the full way, I'm going to save myself the effort of having to write out that down again, because the process is literally the same as in 2.5, so you just look there for the work that I actually do in simplifying this. But at the end of the day, the final solution is going to equal 1 over a times sine squared of pi x over a. We're going to add plus, this time 2 cosine of 3 omega t minus phi. And the reason why I'm sort of changing the order right here is because cosine, remember, is an even function, so we can sort of change and flip the order however we want without actually like changing the equation at all, because cosine of negative x is exactly the same as cosine of x. And then we're going to have sine of pi x over a times sine of 2 pi x over a plus, finally, sine squared of 2 pi x over a. This is getting very messy, and I apologize for that. Okay, and if you compare this with our magnitude size squared of x comma t that we got sort of in problem 2.5, what you'll find is that the only thing that's different is this cosine term. Back there in 2.5, we had 2 cosine of 3 omega t. Here we have 2 cosine of 3 omega t minus phi. And at this point, what we can do now is sort of just calculate the expectation value of x. So we did that in sort of 2.5, and here, since the only thing that's different is this cosine term, and remember that cosine, this cosine term is time dependent and x independent, so it just comes out of our x integral when we calculate the expectation value of x. So because of that, the form for the solution of the expectation value of x is actually going to be exact same as in 2.5, with the only difference being that our cosine term is being changed. So let's just write that out. The expectation value of x, without even needing to calculate, because this is the exact same form just with a different time-dependent function in the cosine, is just going to be the same as 2.5, so a over 2 minus 16 times a times 9 pi squared times cosine, this time, of 3 omega t minus phi. And so the only thing that's different here is our cosine term. Instead of cosine of 3 omega t, we now have this extra minus phi expression at the front. And obviously, just from looking at this, now that this has a phi dependence, depending on what phi actually is, it's going to give us a different answer. If we have like phi equals pi half versus phi equals pi, obviously this is going to give us a very different answer for the expectation value of x. So evidently, sort of the properties of our system, for example position, will actually differ depending on the individual phases of our wave function components. And what I'm going to try to do is to sort of explain why exactly that is. So, as I said before, the goal now is to sort of understand what exactly a phase even is. So we've sort of described so far that any wave function, let's say, well, let's not say any wave function. Let's say, okay, so so far we've learned stationary states, and we've learned that a wave function psi can be decomposed, if it is a stationary state, into a purely time-dependent function, or a purely x-dependent function called little psi, multiplied by a purely time-dependent function called little phi. So we've already seen the form that psi takes. Psi takes on, for the specific case of our infinite square well, square root of 2 over a times sine of n pi x over a. And we already know what phi takes the form of. Phi is our time-dependent function. It takes on the form of a complex exponential e to the I phi, let's just say, or to make the e to the if, and f is some arbitrary function of time. So what we'll find is that, well, the wave function itself will generally always look something like a sinusoid. So the wave function is going to look always like a, let's call this, let's just call this psi. So psi is, this is psi, and psi looks like some sort of wave function. So something like this for our infinite square well. And what we'll find is that this coefficient, this phase constant, which we're calling phi, is something that doesn't actually change the general form of our wave function psi, because remember, psi is equal to little psi times little phi, or just phi, I guess. What phi does is it doesn't actually change the form of the sinusoid. What it does instead is it'll sort of displace it. So this black could be one value for phi. Another, if I changed phi by some value, then my resulting wave function could look something like this, where it just gets displaced forward by some constant. Or if I chose another value for phi, maybe it gets displaced backwards by some constant. So let's see, how am I going to draw this? That is horrible. So all of these three different colors that I've drawn, they're all valid wave functions with the same psi term, with the same little psi term, but they all have different phase constant phi terms. So effectively, phi is just a measure of sort of time, because this wave function is evidently sort of traveling in time, and what will happen is that phi is basically telling us at what time we start actually measuring our function. So the reason why phi does not matter for the larger case, where we just have a single expression with a phi attached to it, is because we can sort of start measuring our system whenever we want. It doesn't matter at what time we sort of analyze our system. So if I have, for example, a wave function that has a, let's say, for example, I have a wave function psi with respect to time, which looks something like this. Well, I can always pick to measure my time at, instead of t equals 0, which let's say is right in the center here, maybe I want to start measuring at t equals 5, and I want to say that t equals 5 is my new t equals 0, in which case, this is my new origin, And because of that, my wave function has now sort of shifted by some constant. So because of that, I'm measuring, I'm sort of applying, that is what applying a time-dependent phi actually does, is it shifts your wave function to the right or to the left by some amount, which is basically the same thing as saying, okay, instead of measuring at time equals 0, I'm going to measure at some other non-zero time. And because of the fact that I'm measuring at some non-zero time, my wave function is going to be displaced by some amount at the end. Now, this obviously doesn't matter for the larger case where we just have a single term, some single psi with some single phi, because in that case, I can just start measuring my expression whenever I want. However, in the case of sort of a problem like this, where we have some psi that is equal to like a combination of like stationary states psi 1 and psi 2, depending on the individual phases of psi 1 and psi 2, because we have to coordinate the times for all three of these systems, t has to sort of remain the same always. What'll happen is that these psis have different phases, and because of that, since big psi is just the superposition of psi 1 and psi 2, if you add the superposition of two sort of time-dependent sinusoids, depending on what time you use to add them together, they will look different. And that is the reason why sort of these sub-phi terms that appear like next to psi 2 or psi 1 will actually change the result of our measurements, whereas something like just an individual big psi times a big phi will not actually affect the measurement. So when phi is applied to the entire wave function equation as a whole, it does not have any physical significance, because we can always measure our system at some arbitrary time, and we can always change the displacement however we want. However, in cases like this, where big psi is composed of a bunch of little psis, and each of these little psis have their own individual phase constants, then these phase constants actually do have physical significance. And because of that, we do have to pay attention to them, because they can, in fact, change certain values that we're trying to measure.